Today I'm going to go over another very interesting and important topic within sequential design, and that is state machine design or finite state machine. Question is, what is state? What is machine? Okay. Um, so things are concept is pretty simple. Okay, we're not developing a machine. It's like it's a way of anyway. Let's look into state. What is state? What do we mean by state? So state is, think of it, I'm just thinking of analogy. Let's say we want to have we are developing a robot. Okay, robot. Okay, robot sometime walks, sometimes, let's say it's a very nice robot, sometimes make tea, cook for us, clean for us. Then yeah, this robot also sleeps. And different states that a robot machine is, those are literally the states. Okay, let's look into when is it's what is right now, it's sleeping. Okay, let's say a robot sleeps. This is a state. So state is typically, we use a circle. Okay, this is a state. And then when this state happens, what do we do? Okay, what robot does? So robot close eyes, and what does it do with legs? The whole body lays back, lays down actually, lay down. So though these are the actions. When a robot is in that state, a robot does these actions. So what happens when sleep? Okay, maybe when somebody rings the bell or knock at the door, then what happens is this robot wakes up. So it gets out of that state, and what does it do? It walks. So we have another state. Okay, in this state, let's keep it simple. It walks. Now it's in walking state. And what does it do in walking state? It opens its eyes and it moves its legs. And this thing happened, bell rang is true. If bell doesn't ring, it keeps sleeping. Bell ring is false. So you see what the states are? Just a way of describing the state of our digital circuit. And key thing here is that when on each state, let's call this box a state, it needs to perform some actions, which are also called outputs. And the next state, current state, and the next state, I put next state here. You will see in a minute why I put here. Soon this will become the current state. So the next mean it's is soon to be the current state. But for now, this is the current state over here. This soon to be current state. I should call, instead of next, I should call soon to be current state. So which is the next state? Okay. And that is determined by some of these variables, which are inputs. So inputs are bell sound. One could be other thing, knock at the door, or alarm, or anything else which can change the state of robot. So now question is, these are the states, and any digital system which performs certain actions. It performs those actions in a certain sequence based on certain things. It keep doing one thing, then when some things change, it goes and start doing another thing. How to sequence those things, and that's where flip-flops come to our help, or storage elements come to our help. So look at this one. It's the same analogy like we explained robots. Our state is like where we are storing some information, is like a flip-flop. So this is our flip-flop which acts as a state. Right now, if it's a 1-bit flip-flop, then we what states we can have? 0 or 1. When it's 0, we do one thing. When it's 1, we do another thing. And that's exactly I put here. So this state, so this is the current state, and this is next state. On every clock edge, this next state, whatever we calculate, whether staying in the same state at this one or changing it, on every clock edge we know that D goes to Q. So our next state becomes current state. Then the next state is calculated, but here we'll give you a better example of a robot, and now in the digital circuit context. So already talk about this is the state, current state, next state. Based on current state, we need to perform some actions, walking off robot or sleeping off robot and all that. It depends on that particular state, and the combinational circuits we create here, we determine these actions from the current state. But how do we calculate next state? By the way, it seems like next state. The next state is determined based on inputs, like in robot case, bell ring, and also depends on what state we were before, so that we can decide, okay, based on the current state and the inputs, here is the next state. But next state only happens when the clock rising edge in this case starts. Hopefully you got that concept. It's very simple. Three things. Okay, flip-flop, combination circuit to generate next state, and combination circuit to generate outputs. That's it. Now this type of state machine where output actions are generated only based on the current state is called Moore state machine, or Moore finite state machine. And we will also study the other example. The other example is, let's say, easy to copy this. Oops, here, where actions also depend on inputs. So inputs coming here also connected to outputs. That is called Mealy. I hope my spellings are right. Mealy state machine. Anyway, in this example, or maybe in this video, next video, I don't know how long it takes me to go over this example of Moore state machine, we will talk about only the outputs are generated based on current state. Okay, I think that is the overview. Okay, now important thing is states can be many. Like I said, if I put one flip-flop, I will have 0 state and then move to another state. Only 2 states. I'm staying here or moving between them, but these are only 2 states, because this single flip-flop can be 0 or 1. But what if I have more? What if I have 4? Then I need to represent them with 2 bits. So then I need, these one needs to be 2 bits, because then I will have these 4 combination. This one state, this is another state, this is another state, this is another state. So how many flip-flops we use, that's really that is based on how many different states we need to have. This is one. Okay, I want to put an example here, and this example I am using exactly as is from this book, Digital Design and Computer Architecture, second edition, David Harris and Sarah Harris. Okay, so very good book. I'm using example as is. In this example, let me explain what's happening. What we will do is we will create a traffic light controller. I think this is a very good example. I don't want to skip this. I want to go through this because this is a practical circuit that we are creating now. Now that we have gone through combinational circuits, sequential circuits, now we are developing a practical circuit that has application there. So let's do this in example. And what we will do is I will make use of Moore state machine, how we can sequence things, how we can sequence between different light generation. So this example, we have a crossing. So this is a crossing inside a university. So the students areas are okay. There's a dining area, there's cafeteria, a restaurant area, and then on the south side we have athletic fields. So student, whenever they are from here walking there, or from there coming here, they're walking here. And then on the west and east side you have labs and student dorms here. So there's a pretty regular traffic. Students are walking there, having a chit chat, busy with their own things. And what we want to do is we want to install a traffic light controller here, so that whenever, for example, students are coming from this side, there are students here, it stops any cars or other traffic coming from that side to avoid any accidents or any injuries. So what we want to do is we want to put this type of, I drew this myself, by the way, copy, and we can paste. I need to make it small. Can I make it more small? We have one here, not in the middle of the road. Of course we will have a properly installed bus. I want to put it in the middle so that you can understand. One here, one here, one here. Then we need to put sensors, right? So here's my sensor. I didn't create that. I copied that. Duplicate. We want to put, oops, it's an image. Can I put it here? Okay, it's fine. There's one here, one on this side. It's okay, let's put it like that. One on this side, one on this side. Okay. And what we are doing here, this sensor sense that there are students coming from this side. This one will sense there are students now on this side. Similarly, this one, these ones are from this side. Okay, hopefully that is clear. So we have sensors and we have traffic light. So when we see a traffic pedestrians here, students coming here, what's going to happen? These two will go into red, so to stop the traffic there, and so that these pedestrians will go past this. Understand? Okay. All right, so what do we want to create? What I'm calling here, maybe bring this one over here. Yeah. Okay. What we want to have a controller, not that one. This controller here, a digital controller. The inputs are TA and TB. This and this is I'm calling TA. Either of the sensor we need to turn this thing, these controllers into red. And TB, these two are called TB. Whenever they sense pedestrians, they need to make this one red. Understood? So there are only two. So not TA, B, C, D, this and this TA, this and this TB. And based on that sensor, we need to generate LA, light A, light B. So this one and this one together I'm calling light A, because even though we need to generate a signal for this, but you will see that we need to kind of turn them into on and off same time. The other inputs are reset. We want to start this our state machine in a particular state. Very first time when we switch on the power, what state we go in. And then we have a clock. The clock is important because with respect to clock, that clock will go to the flip-flops and we will be making the scene on the rise edge. Next state will become current state on the rise edge of the clock. And the period of clock is 5 seconds. So every 5 seconds we are determining, okay, what do we need to do with these controllers. Got it? So that is the overall circuit. And I think I'm gonna stop this video here. I try to avoid making very long videos. Try to go over it, what I'm trying to do, and in the next video, hopefully we'll complete our controllers. We need to determine LA and LB, and also need to determine on the state inside. All right, that's it for now. See you tomorrow.